Thank you, everyone. This talk is always a pleasure to give, and I want to encourage your questions during the talk. Sometimes I get too many questions, and then I'll say, okay, we'll talk more about that at the end. But in general, please ask if I'm going along and you're either not understanding something or you just want to know more about something. I think this is NASA's most exciting mission of the last few years, maybe along with Curiosity and other Mars rovers. But it certainly this is a time in the history of humankind where we are, for the first time, learning about planets, how many planets there are out there, how common or rare is a planet like the Earth. I was a science fiction fan growing up, and I still am, actually. And so that's a real big question. I used to watch Star Trek. They didn't have any trouble finding planets to investigate. And the question was, is that pure fiction or is that probably the way it is? And so the Kepler mission really was designed to answer that question. Probably many of you know that we actually haven't known about any exoplanets until 1995. And then for a while, the methods that we were using to find them really concentrated on large planets, gas giants like Jupiter, especially if they were close to their stars. So nothing like the Earth, really. And the Kepler mission really is the first major mission to be able to study the question about what about terrestrial or rocky planets like ours. So I'm going to tell you how the mission works, and then I'm going to tell you what the main results of the mission are. That's basically my talk today. So how does it work? Well, first of all, this is the Kepler telescope, and those of you who still read newspapers or check the news on the net this week will have read that unfortunately the Kepler mission is now defunct with respect to its primary mission, that is the mission of figuring out how many planets there are out there. It did fulfill its goal of doing a study for 4 years. So we got 4 years of good data, and then the gyroscopic pointing controls are no longer working on Kepler. This picture actually is correct in the sense, you'll notice here's the Earth and the Moon. Kepler is not orbiting the Earth. It's actually in solar orbit. It's trailing the Earth. It's gotten about a third of the way behind us in our orbit at this point. So that's where it does its work from. So basically from Earth orbit, but not from around the Earth. And it's just a telescope that looks out. And I'll explain how it works. But what it's looking for is, in a way, what's in this picture. Although naturally it cannot resolve stars in the way that this picture shows. So this is our star, the sun. That's a shadow of a blockage caused by a fisherman on a pier. That's a pelican. These are clouds, and that is the planet Venus. So that is an Earth-sized planet, and in the process of transiting the solar disk, and that is the methodology that Kepler uses. So we are looking for that event to occur around other stars. But of course, stars are all just points of light, and so I'll explain how it uses transits to find planets. This is really the only good way right now we have of detecting planets the size of the Earth. The other methods that are used don't really work for planets that small. So let's talk first about transits and how you use them for detecting planets. The concept is really simple. If you are so fortunate as to be sitting in a place where you see a transit actually pass in front of the star that it's orbiting, then it's going to block some light from the star while it is projected onto the stellar disk. And of course, that won't necessarily happen. In fact, most of the time that won't happen. Planetary systems in the galaxy are oriented randomly with respect to any coordinate system you want to think about. So they're not all aligned with the Milky Way. They're certainly not all aligned with our solar system. They're pointed in arbitrary directions. And so for most planetary systems, the planets are in an orbit where they'll never appear to cross in front of their star as seen from the Earth. But it's not hard to calculate how likely it is that that's going to happen. I'm not going to go through the math here for this audience, But let me give you the answer. The answer is the probability that you will see a transit is just the diameter of the star divided by the diameter of the planet's orbit. That's the chances that you will see a transit. And so for the Earth, which is a couple hundred solar radii away from the sun, the likelihood that somebody sitting in some random star system elsewhere would see the Earth transit the sun is about 0.5%. So that's good news and bad news. That means that it's not very likely that it will be seen. On the other hand, if you see it, then you can say, that only happens, I only see 0.5% of these, so I get to multiply, every time I see one, I get to multiply that by 200 if I want to know how many planets there are out there. Okay? But the number I get to multiply by is this factor here. So for very close-in planets, the diameter of the orbit is that much bigger than the diameter of the star. The probability can get up to something like 10%. So we'll see 10% of planets which orbit with few-day orbits around their stars we can detect with the transit method. Okay? So that's the one thing. What that means in terms of mission design is I better look at a lot of stars, because for most stars that have planets, I'm not going to see a transit. The second question is, what am I going to see? So I do not see a stellar disk when I look at the stars with the telescope. All I see is a point of light. And there's no chance at the moment that we're going to resolve a disk and see a little black dot moving across it. So that's not what we're looking for. What we're looking for is just the effect of that. So this is called a photometric light curve. That just basically means a history of how bright that point of light appears to be. And so the star, if we assume the star has constant light, which is not a correct assumption at the level of precision Kepler has, but start there, then it's just going to be constant. And then we'll just notice that suddenly the light decreases, and then after a little while it increases back to the former rate, and that's it. So that's the signal we're looking for. So that just means that the Kepler telescope needs to be very good at measuring how bright stars are. It needs to measure them to quite high precision. I'll say how high in a minute. Do you have a question? Yeah.
Yeah, is there a common factor to determine the distance of a planet is from the star? Its surface, like mass? Is there any common variable?
There's nothing to say how far a planet is going to be from its star. In fact, that information is part of what we learned from the Kepler telescope. So what we learned basically is I'll explain how we learned that. But that is one of the things we find. So we are being told by the data what the distribution of planet distances is. There's no theory that tells you what it ought to be. Okay, so how much of a dip is this? It turns out it's also very simple to figure out how much of a dip it's going to be. It's just the area of the planet divided by the area of the star. That will be the amount by which the light decreases. So here's a simulated picture of our sun with Jupiter crossing it. And so you can see it's walking, Jupiter's about 1/10 the radius of the sun, but its area, so you have to square that. So it's 100th of the area of the sun, which is about 1%. So if I measure how bright the sun is to 1/10%, then it's very easy to see a 1% dip occur. On the other hand, this is an actual picture of the transit of Venus in 2004. How many people here saw the transit of Venus either in 2004 or 2012? Okay, maybe 15%. The rest of you, I'm sorry to say, you missed it forever. So it happens twice, and then it doesn't happen again for about 150 years. So unless you're planning on living for another 150 years, you're out of luck. But this is what it looked like. And we saw it from Berkeley. I saw it standing out on the plaza there. But you can see that for a planet Earth-sized, that's only about 1% the diameter of the sun, and I have to square that, which means 1 part in 10,000. So the light level, if the light level is normally 1, it dips down to 0.9998 or 9999 of the brightness of the sun when the Earth appears to cross it, or Venus appears to cross it. Okay? That is tough. To measure the brightness of a star to 0.01% is really actually basically impossible if you sit on the ground, because our own atmosphere is murky enough and turbulent enough that it changes the brightness of the stars by more than that. You've seen something akin to this in the twinkling of stars. So they appear to change their brightness even to your eye, right? And that's much more than 0.01%, believe me. So you need to get above the Earth's atmosphere, and that's why this is a NASA mission. Okay? We don't want the atmosphere in the way. And in fact, we don't actually even want the Earth and the Moon to be nearby, changing the illumination on the spacecraft or its temperature slightly or anything. You need everything to be really, really stable and quiet in order to do this measurement. So you go up into space and you get away from the Earth, and then that also means that you can look all the time. So there are no clouds going by, and especially there's no day-night. So why do we care about that? Well, let's think about this again in terms of the Earth going around the sun. It turns out, and those of you who saw the transit of Venus know, it took place in a few hours. So at the orbital speeds of the planet, at distances like ours and a star like the sun, it's moving fast enough to appear to cross the solar disk in a few hours. Okay, and then it's going to come around in its orbit and do it again. The reason it doesn't do it again for Venus and the Earth is that Venus and the Earth are pretty close to each other, and so our perspective is influenced by the tilt of Earth's orbit and Venus's orbit, and so it just happens to miss most of the time Venus seen from Earth. But if you're off on another star, either you're going to see it or you're not going to see it. Let's say I measure this for the Earth going around the sun. How long do I have to wait before I'm going to see it again? Someone. 1 year, right, exactly. So that doesn't happen very often. So it takes a few hours, and then you have to wait a year. And suppose you don't know the orbital period, and you don't know whether this given star is going to do that or not. So you see the problem. Like, for example, if you're doing this from the ground, you lose half the time, because half the time it's daytime, right? So you can't do this during the day. And then there are clouds some nights and so on. So transit experiments from the ground are way, way less effective than transit experiments from space, just because of the duty cycle. You really need to be looking all the time. And so the Kepler instrument is very simple in that sense. It's essentially a camera, a little bit like your cell phone camera. It uses the same kind of detector, somewhat higher quality for Kepler, and also quite a bit more pixels, but it's a 98 megapixel camera. And it looks all the time at the same stars, never looking away, never points anywhere else, never does anything else. It just basically takes a picture of the sky constantly and measures the brightness of the stars in that picture, and then just keeps doing it. And that's why, because you need a high duty cycle. Okay? Other than that, if you've got this level of photometric precision, you'll see it. Yeah.
Which stars?
Which star? I'll get to that. Where should we look? And it turns out you can look pretty much anywhere. It's robust, but you have to be patient, especially if you're looking for Earth analogs. Now, if it's a planet that goes around its star every 10 days, then that's not as bad, right? So every 10 days you'll see this signal. You really want at least 3 transits. Why? Well, the first time you see it, you say, oh, that's interesting. That kind of looked like a transit. But as I said, it turns out stars have all kinds of reason to vary, and by more than that. And so you're not sure. Was that something the star did, or was it a planet? The second time that it happens, you say, oh, I see it again. It looks just like the last one. That's a much better indication that it's probably a transit. And now, actually, I know what the time between them was, so I probably know the planet's orbital period. Okay, but probably is not really good enough. I need to confirm that. So I need to see it a third time. Right? So then if I see 3 events that all look the same, and they have the same spacing, the first, the second, and the second, and third, now I'm in really good shape. It's an astrophysical event. It turns out it might not still be a transit, but we'll get back to that too. Okay? All right, so actually it's a very conceptually simple experiment. And so this is the Kepler spacecraft. It's really, as I said, just a big digital camera, or if you like, a telescope. It happens to have a lens at the front end of it, unlike almost all big astronomical telescopes. That's to give it a big field of view, because I want to look at a lot of stars. So for those of you who are more expert, it's a Schmidt telescope, which just means it has a wider field of view. So the Hubble Space Telescope's field of view is, a tiny piece of the moon. The Kepler's view is about the size of your palm if you hold it up to the sky. It picks up that much of the sky. So it gets a lot more stars. So we want to basically monitor 150,000 stars. There's several million stars in the Kepler field. We pick out 150,000 to monitor. And the rest of this gobbledygook just means the photometric precision needs to be good enough that even a 1 in 10,000 dip is not swamped by the noise of the instrumental detection. So you need to be better than 1 part in 10,000. You really want to be like one or 2 parts in 100,000 photometric precision to do this experiment. So it turns out Kepler did achieve that level of precision. Other than that, it's a really simple thing. As I said, it always points in the same direction. The solar panels are just kind of stuck on the side of it. And so the only thing it does is every 3 months, it rotates 90 degrees because it's going around the sun, right? And it wants to keep the solar panels pointed towards the sun. So 4 times a year it turns by 90 degrees just to keep the panels there. And the focal plane is 90 degree symmetric, so you get the same pictures, it just lands on different CCDs. Yeah?
Where were those wheels?
Oh, the wheels are in this part of this is called the spacecraft bus. So there are 3 gyroscopes in there. Let's see. It's labels thruster modules. I see them on here. So the way pointing for spacecraft work is you have 3 gyroscopes in the 3 different directions. And if you want the telescope to stop drifting this way, you apply a slight brake to the gyroscope going the other way, and it comes back. If you keep doing that, basically, there's nothing to hold on to. So every so often, you stop momentarily, and you spin the wheels back up, and you don't want the spacecraft to spin in the opposite direction, so you fire a thruster against the wheel, get the wheel spinning again, and then you can just torque on the wheels. And so what happened was there were 4 wheels on Kepler. One of them failed about a year ago, so we're down to 3, and we knew we were probably in trouble since 1 failed. The second failed a few months ago, and so that was the end of it. Yeah, back there.
Yes. How do you keep track of so many stars, light from them with one detector? How do you separate it out?
Computers. So the light that comes in through the lens, it bounces off the mirror, and then it just gets focused on this array of CCDs, which is the same detector as in your cell phone, and you get a picture. I think I have a picture that I show, but so you have a whole bunch of bright dots on your picture, and you know which stars they are, and you measure how much signal came for each dot. And then one way to think about this is you have 150,000 of them, and they're varying up and down due to stellar and transit effects. But the average of all 150,000, that's pretty fixed. And so you can measure the brightness of each one against that global average to get a good measurement. We only care about the about the changes in brightness, right? So you can always pin it to the average. That's not how it really works, but that's close enough. Yeah.
Does the light from one star typically just hit 1 pixel, or maybe a couple of pixels, or?
Yeah, actually, the design of a funny story. The design of this telescope is to defocus slightly. So this does not take super sharp images like Hubble, because you really don't actually want the light from the star to go onto 1 pixel, because 1 pixel, if the telescope jitters slightly, which it jitters at some level, and so a small amount of the star starts missing the pixel, you'll see that as a brightness change. So actually we defocus a little bit so it lands on a few pixels, and then you can average that and work with it. But actually, even that is subject to effects which we are still struggling with. So the fact that you have discrete pixels is a problem, but It hasn't stopped us from doing the science. Yeah, one more question, then I should move on.
What wavelength of light does it detect?
Yeah, it's just broadband visible light, so it works a lot like your eyes. It covers the visible part of the spectrum. It does extend into the red part beyond where your eyes work a little bit, but it's not an infrared instrument or anything like that. Okay, so somebody asked, where should we look? Well, we want to know the frequency of planets in the galaxy. So where should we look? Well, it turns out that in order to do the experiment properly, you need stars to be reasonably bright, and by reasonably bright, for those of you who know the magnitude system, it needs to be brighter than about 15th magnitude, which isn't very bright. What it means essentially is that the stars we're looking at need to be within a couple thousand light years of here. Well, stars in the galaxy actually drift around with respect to each other, and you wait a few billion years and they're kind of mixed up. And so it doesn't really matter where you look. You're getting a random sample of stars. So there are other considerations that come in. This is a map of the whole sky. Here's the path of the sun through the sky. I don't want to look there. I'll fry the telescope in a hurry. Besides which, as you saw, I need the telescope. The solar panels are kind of perpendicular, so I don't want to look at the sun. I don't want to look. In fact, I don't want to look anywhere in this band or this band to have the spacecraft oriented properly. So I either want to look up here or down here, and I want a lot of stars. Well, where's the best place to find a lot of stars? The Milky Way. Right? That's tons of stars. Actually, it's too many stars. So you actually want to be a little off the Milky Way, but not much. So here's the Milky Way in this projection, and here's the avoidance zone. So let's just look either near the avoidance zone boundary and near the Milky Way. You look there. You could have looked over here, maybe here. You could also look down here, but that's visible to the southern hemisphere, and we're all in the northern hemisphere. So it's like, no, we're going to look where we can use our other telescopes. So that's where we look. And where that is in the sky is this. So those of you who know the summer triangle, we're looking in sort of, here's the summer triangle. It's this bright star, and that bright star. There's the Milky Way. So as I promised, we're looking slightly off of it. So if you know Lyra and Cygnus, or the Northern Cross, we're looking basically between them. Okay? And those squares on there are the projection of the CCD detectors onto the sky. So it's the stars which land in there, or here, that we are looking at. Otherwise, it's a random sample of stars. If you take the galactic point of view, this is what we're doing. So here, we're in the galaxy, we're sort of out in the 2/3 of the way from the center, so we're sort of out in the suburbs. And we didn't want to look at the Milky Way, which would be looking that way. We didn't want to look at the galactic center for sure, so we don't want to look that way. The Milky Way is this disk of stars projecting into the sky is the Milky Way, so we want to look just a bit above that. So we're looking out like this, and about 3,000 light years out to pick up stars that are bright enough. So we're looking in that cone. That's where the planets are being sampled. Yeah.
What's the sun's angle of orbit relative to the plane of the Milky Way?
We aren't inclined much to the plane. We have an excursion of about 50 light years up and down compared to the central plane as we go around. So it's a small number of degrees. Okay, so I said that I explained what you're looking for to get a transit, and if you see 3 of them and they're all the same and they have the same period, then it's probably a transit. Except there's one other astrophysical false positive, which has been a problem, but we knew it was going to be a problem, and we have figured out how to eliminate, basically, which is you may get the same signal, but it's still not a planet. So, for example, and these may seem like contrived situations, but actually they happen fairly often. So it turns out, if you look at a random star in the sky, chances are about 50% that it's not really one star, but 2 stars. So stars come in pairs quite often. It so happens that our star is not paired up, But that's, only about 50% of the time true. So suppose I have a G star like our sun and an M star, which means that it's smaller than our sun, half the mass or less than our sun, which is a lot fainter. So when I'm looking at the star, I basically just see the G star. The M star might be 1,000 times fainter, so it's sort of a 0.01% or 0.1% effect. And let's suppose that the M star has a Jupiter-sized planet going around it, for example. Okay, so I get the combined light from this whole system. Most of it is the G star, which is constant. Then there's this faint M star, and then it experiences this regular, same depth eclipse or transit due to a Jupiter-sized planet. Well, I add all this up because I don't know. That's what I'm looking at, and I get this. And that looks like an Earth-sized planet orbiting the G star. So that's one kind of false positive. Or it might be that I actually have two stars. So maybe this isn't the planet. Maybe that's another star. So I could have two stars orbiting each other and eclipsing each other. And then I take that system and I put it way back. So let's put that one at 8,000 light years away, but line it up exactly with a star that we think we're looking at, or we are looking at it, but we don't know there's another one lined up right behind it. And it's eclipsing. So again, you'll get a regular, repeatable signal, but it's not a planet. And so when people talk about the Kepler results, they talk about two things. One, they talk about the planet candidates, and then the other one, they talk about confirmed planets. So when we say confirmed planets, we mean we have tested really strongly for all of these situations, and we've been able to eliminate them. So we're sure that it's a planet. In some cases, we may also actually see the effect of the planet pulling a star using the wobble or Doppler method, and then that's of course much better. Most of the Kepler results right now are planet candidates, and we have about 3,500 planet candidates. And so the way we're thinking about this right now is doing tests on samples of Kepler candidates. How many of them turn out to be false positives? And the false positive rate is around 10%, and it's been tested various ways. And so when you hear 3,500 planet candidates, you should say, okay, and probably 350 or 400 of those are not real. But of course, that leaves 3,000 that are real. And so that is what you should think when you hear about Kepler results. Yeah, you have a question?
Yeah, I was wondering if there's any reason why you can't have a double planet, each of the other's moon?
You could also have that.
That influence this, right?
Well, that one's trickier because if you have let's say, we can go back to Star Wars. You probably are aware that Kepler did find Tatooine. So there was a planet which was orbiting a double star. So you have two stars and then the planet going around both of them. We also have situations. So you could have a situation where you have a star and a planet, maybe Jupiter-sized, and maybe an Earth-sized moon going around it. That's I forget which planet that is in Star Wars, but they have that situation too, and there's no reason why you couldn't have that. In that case, though, the orbital period of the planet around the other planet would be much faster than the orbital period of the big planet around the star, and the signal size is going to be quite different because the one planet going around another, it's not blocking light from the other planet. So they both have to block light from the star. And so then you'd have a big transit and a little transit associated with it, right, as they both go by. So people are looking for that, actually. We haven't found any yet, but in principle you could find it. In practice, that one's pretty hard to do.
That'd be like us and the moon if the moon was bigger.
Yeah, or if we were Jupiter-sized and its moon was Earth-sized. Of course, Ganymede is bigger than Mercury. And we have found Mercury-sized planets with Kepler. So it's not that we couldn't do it, but it only would work for the very brightest stars in a really favorable situation. So actually, while we're on the topic, the other thing you could see would be Saturn's rings, especially if they were a little bit thicker, right? So if you have a ringed planet, and the ring plane is tilted so the ring really blocks the star, you'll get the ring occulting the star first, and then the planet and the ring, and then the planet will leave, and you'll have the other part of the ring. So you get these funny little ends on the transit. People are looking for that too. Okay, so what are the Kepler results, having now been primed? We found a lot of planet candidates. Even by February 2011, when the first pass was done, it was clear that there were a lot of planets. But more importantly, there are a lot of small planets. Okay, so let me take you through this a little bit. Here, this is a plot of orbital period versus size, and size relative to the Earth. So this is the size of the Earth here. Here's the size of Neptune. Here's the size of Jupiter. The first harvest of planets in February 2011 are the blue points. And you'll notice they are mostly big planets. Why? Because those are easy. Right? I mean, they hit you in the face when you look at the data. Oh, there's a planet. Whereas these are much harder. So the second release is the red points, and you see we started dipping into the small planets. And the third release is actually concentrated on small planets. So this is kind of where we are right now. Yeah.
What do you mean by a release?
So February 2011, the spacecraft was launched in March of 2009. So that's 2 years into the mission. You now have light curves or photometric histories of 2 years, which you could then sift through looking for transits. You don't know, how long the orbital periods are. So basically, at that point, you were pretty good at picking up. Remember, I said you needed 3, right? So you have to divide 2 years by 3. So basically, half a year orbital periods were about as good as you could do. And those only have 3 transits, whereas 10-day orbital periods, by now you have, 20 or 30 of them. So you can pull them out of the noise better. So basically, as time goes on, you can pick out smaller planets because you have more transits to average together, and also longer period planets because now you've picked up more transits. Whereas, a planet with 1 year period, you couldn't possibly detect that after 2 years because you want 3 transits.
But it still seems like a continuous process. Why was it bundled into?
Oh, well, in principle, it's a continuous process. In practice, it's a bunch of people sitting down and cranking through a lot of computer programming, which, since you're searching for arbitrary-sized planets with arbitrary orbital periods, takes a good deal of processing. Plus, you have to deal with all the things the stars are doing to you. So it's not an easy process. So astronomers work for a few months, and then they get a result, And then that was for quarters 1 through 5, And then you do it again, but now you do quarters 1 through 8, but you need to do them all. So it comes out in batches for that reason. All right, well, what did we find? First of all these planets that were, the wobble method was very good at finding, were this kind of planet. So big planets with short orbital periods. So indeed, we found a bunch of them in the first release, but it became clear that's not the usual kind of planet. Now we knew that because we knew the Doppler method is very selective. The transit method is also selective in the same way, mind you. So the bigger a planet is, the easier it is to find, and the closer it is to the star, the easier it is to find because the orbital period is short. So we both suffer from the same selection effect. And you need to keep that in mind as well. So it's not as though this result tells you what the distribution of planets, period, is. This tells you what the distribution of planets that our detection methods can see is. And so far, those are mostly planets that are relatively close to their star, and we're better at finding bigger ones. But, Kepler was all about finding smaller ones, so we try really hard with those. So here's the distribution of planet sizes in the Kepler sample. So actually, planets bigger than Jupiter are pretty rare. This is planets sort of Jupiter-sized here. Neptune-sized planets, actually, are the most common planets that Kepler sees. But remember my warning about selection effects. It could be that Mars-sized planets are more common. We wouldn't really be able to say. But in the Kepler sample, Neptune-sized planets are the most common. Those are, 4 times bigger than the Earth, about 10 12, 15 times the mass of the Earth, and they don't have solid surfaces. So they have enough of volatiles and gases that when you go to that planet, it's not rocky until so far in that you wouldn't call that in any way the surface. So if you try to land on the planet, you're going to plunge through, an atmosphere and then into thicker and thicker soup, basically, until you get crushed somewhere. So those are not the kind of planets we were really looking for, but that's what nature makes a lot of. Then there are these, which we call super Earths or mini Neptunes. So our solar system doesn't have any of these in it. So we have Earth and Venus, which are basically the same size, and the next thing we have are Uranus and Neptune, which are basically the same size, and nothing in between. But we couldn't think of any reason why nature shouldn't make things in between, and indeed nature does. So actually the super Earths are the next most common, but remember, it's harder to find Earths than super Earths. So I'm going to show you a corrected plot later on, but this is what we actually see, like this. Okay, and then they're very much favoring the shorter orbital periods. Again, that's just because the way the experiment works. So I couldn't say what the distribution of planets out here is, because I haven't been able to measure them really so far. Okay, so what about these super Earths or mini Neptunes? And where should I stop calling it a super Earth and start calling it a mini Neptune? Well, probably, if it's got a rocky surface, I want to call it a super Earth, and then when it doesn't, I don't. And right now, we think that boundary is probably somewhere around 1.5 times the size of the Earth. That's the size of the Earth, or it's a few Earth masses, okay, where the evidence, and I'll explain what the evidence is so far, suggests that you go from a rocky planet to a mini Neptune. Okay, so it's one of these. And actually, these things, for a while anyway, so Neptune has a thin layer of hydrogen and helium, the way that Jupiter and Saturn have a thick layer. Below that, it's basically water. So if you want to think of it as a water world, you could. It's water mixed with methane and ammonia. Water is a very common molecule in the universe. So, people say, you want looking for life, follow the water. Well, there's water everywhere, basically. Well, there's a lot of water out there. You can, in fact, build bigger planets out of water than you can out of rock. So water is a more common building block or available material, if I'm making planets, than rock is. And so it's not surprising that as we go to larger planets, we go to these planets that are water or gas-based. There's just more of that in the original solar nebula. I'm not going to explain this, but people can do models in which you say, I'm going to build a planet out of 3 basic ingredients. I'm going to have a core, which is iron, usually, for reasons I can't go into, but, and then I'm going to have some kind of a mantle, either, silicates, basically, silicon, oxygen, that kind of stuff, like our mantle on the Earth. And then I'll either have basically the solid part of that on the outside where it freezes, which is the crust, which doesn't really matter here. Or I'll have another mantle, if you like, of water, basically. And depending on how you construct this planet, so this is, core, percentage of core. I can go from 0 to 100% core. I can go from 0 to 100% water. I can go from 0 to 100% mantle. And then if I say pick 5 Earth masses, I can calculate how big that object is going to be, depending on how I make it up. Okay? And Kepler tells us how big the planet is. I guess I forgot to say, what does Kepler tell us? So by the depth of the transit, we learn the ratio of the area of the planet to the area of the star. Area of the star, we are reasonably good at getting independent of something like Kepler. So we take a spectrum of the star, measure its brightness, etc. We know fairly well, and by fairly well, to 30%, how big the star is. And so then that gives you the planet to 30%. The orbital period, and the reason the mission is called Kepler, is Kepler's laws, Kepler's planetary laws, tell you that if I know what the mass of the star is, and I know the orbital period, then I know how far it is from the star. So that was the answer to that question a while ago. So from the orbital period, we get the distance. Once we know the distance, we can also calculate how hot the planet is likely to be with an unknown factor due to what kind of atmosphere does it have. Okay? So that's kind of what we can learn just from Kepler. And so you can get size, but that doesn't really tell you the whole story. You really want to know what's the density of the planet at least. And for that, we have to then go to the older method, the Doppler shift or Raman method, which depends on the fact that if you have a planet orbiting a star, the planet actually pulls on the star. It pulls on it a little bit as it goes around, and we just measure the motion of the star due to the planet pulling on it. And of course, the bigger the planet is, the more it can pull on the star, and so we can get the mass of the planet basically from that. So you then, once Kepler finds a planet candidate, you want to go, if you think it's a pretty good candidate, you've eliminated the false positives as best you can so that you're willing to spend time on it, and then go try to measure the mass. And so we've done that for some number of planets. So if I know the mass and I know the size, then I can get the density. And if I combine the density with those model planet things, I can get some idea what kind of planet it is. So that can't be done for most of the Kepler candidates. It's been done for a few. So here's a planet mass radius diagram. So this is again the size of the planet. Here's Earth, Neptune, and Jupiter. And this is now mass of the planet. So that's one Earth mass. There's Neptune is 11 or 12 Earth masses. Jupiter is like 300 Earth masses. Okay? And then these curves are what the theory tells you where planets of different compositions ought to lie in this diagram. So a pure iron planet, for example, should lie here. The Earth should lie along a curve like this. So if I start making the Earth more massive but keep its composition the same, it would move along this curve. This is more Neptune-like planets here. And then these are actual measurements. All these points are actual measurements from Kepler and Doppler of where planets sit. So you see there's a bunch of Neptune-like planets, as we said earlier, and they fit with this structure model as well. And then we have some Earth-like planets in there. Yeah.
What are the four little white guys?
Oh, these are planets in our own solar system. So that's Earth and Venus, and that's Uranus and Neptune. Yeah.
You mentioned the Doppler effect of a planet that you know is circling a star. How do you know that that effect is due to that planet and not other planets that are circling the star that you don't know about?
Because we know the orbital period from the transits, and the Doppler effect had better have the same orbital period. If you're going to ascribe it to that planet, it better operate on that period. But actually, that's a good question. So then, we didn't really talk about the fact that there might be more than one planet, and actually they might transit. More than one planet might transit. Yeah.
One kind of strange thing in reading about this in several sources, I see this citation of the number of planets discovered by Kepler, and I hear discussion of different methods, but I don't see a straight quantitative comparison. How many planets have been discovered in all, and can you break that down by number?
Well, I'm giving you what we have. So we have 3,500 candidates. We know what size they are and what their orbital period is, so we can group them in that diagram that I showed.
No, I mean by others. How much has been done by others relative to the size of the database you've got?
Nobody else has found 3,500 candidates. I actually, there's a very nice slide deck which the mission scientist showed at Lawrence Hall of Science a month ago that I asked her to give me, that she didn't give me yet. So, which starts overlaying, here's what Doppler method has found, here's what ground-based transits have found, and then blanc, here's what Kepler has found. So that's how it goes, basically. Okay, so our solar system is basically laid out in a plane. I said there was slight tilt between Earth and Venus's orbit, enough to make it miss transiting most of the time. But that's only a couple degrees. So if I stand off at a long distance, depending on what distance, again, the planet is from the star, I might pick up more than one transit. The record is now 8. Kepler has found a system with 8 transiting planets. And of course, it turns out that if there's more than one, that's a great way to eliminate false positives, because you can infer the properties of the star from each of the planets separately, or they have to match with the properties you think. So if you have more than one and they work with the same star, that's a very good elimination of these other weird false positive possibilities. So here's one of them. Here's a six transit system. So how do we sort it out? Well, first of all, the transits have different depths because the planets have different sizes, and secondly, they have different orbital periods, so they occur, at different rates. So here's a big planet which occurs there and there. Here's a smaller planet which occurs there, there, and there, an even smaller planet which occurs there, 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 and there. So you can figure it out pretty quickly. That system is amazing. So here's our solar system with Mercury and Venus. And here's that system. It all fits, it's barely bigger than the orbit of Mercury. And you have 6 planets in there. And their sizes, this is one of those diagrams that I've shown you already. So this color crosses are the planets in Kepler. Kepler 11. Right? So this is a sort of bigger than Uranus planet. Here's one that's kind of like Uranus and Neptune, but lower in mass. Here and this too. All the ones with letters on them. This one is not quite Earth-like, but it's like a water world. And they're all packed in there. And they're not in order of size either. So this has given planet formation theorists a real headache. That's not supposed to happen. Yeah.
When you're looking at a group close to a star, if you want to know whether life is possible on it, you have to know how close it is and how bright the star is. So is something like that possible, or is it?
Yeah.
Are they all just too close to the star?
Well, these are all too close. Yeah, because this.
But you find others that are just right.
Right. This particular star is like our sun, and so if I try to live on a planet that's between Mercury and Venus, kind of out of luck. Never mind which. None of these probably really have solid surfaces either. Although maybe that's good for this kind of situation. Maybe. Well, let me not speculate. Anyway, we do know how hot those planets would be, and we kind of know how big they are, and so on. So we have a fairly good line on what those are. They're not habitable planets. Yeah.
If the orbits are like racetracks,
yeah.
do the planets tend to clump up, or it's just random, or?
Okay, that's a very good question. So they all go around at different speeds. The closer they are to the star, the faster they have to go to not fall in. So it's like a racetrack in that sense. That's why these orbital periods tell you how far it is. So at any given distance, you have to move at a certain speed to be in orbit around the star at that distance. So that's why we know where they are. Okay. One thing that does happen though is when you pack them in like this, they do feel each other. So the inner ones go by the outer ones at a faster speed, and if they have enough mass and they're close enough, they will pull on each other, right? They have gravity too. And we actually see that. So the transit timing will get thrown off. As I'm coming around, if another planet is here and it pulls me forward, I'll transit sooner than I expected. Or if I'm ahead of it and I'm getting pulled back, I'll transit later than I expected. So those are called transit timing. That's a transit timing method. You can pick up actually planets that don't even transit that way, because the planet that is transiting is being delayed and accelerated by some unseen body in a regular way, and you can actually infer what that body is and where it is. And that has now been done for 50 systems, where we actually see transit timing variations. That is a guarantee that it's planets, right? Because that all has to work out exactly right. Yes?
I was just wondering, is that what's going on in that, why the little blip is closer to the big blips on the...
No, all that's happening here is that the period of the little one is faster, and it's just ticking along. it doesn't really care when the others tick along, except that if I were being very careful, I might show that the red arrow is slightly delayed and slightly ahead, depending on who it's near. Right. So those do get picked up. Yes?
I have an explanation, I think, for the randomness of the distribution of sizes and so on in those very close-knit planets. There is an analogy, and that is the satellite systems of the larger planets of our solar system. And what they show is a clear, regular spacing in the middle, and then really in close and really out far, it gets very irregular. And you see that very irregular in the solar system too, of course, the outside, but the inside is too hot.
Well, the formation of moons around Jupiter and whatnot isn't quite the same as here, so you're partially correct. Our explanation is that planets shuffle, so they don't stay where they are when they form, basically. So, for example, these hot Jupiters, we don't think any of them formed there. It's really possible to form a Jupiter-sized planet in a 10-day orbit around a solar-type star. So they move around. They get carried in by the accretion disk. They interfere with each other in a way that's not subtle like this one, but there are secular resonances that occur, and planets get thrown out of the system altogether. They exchange places, etc. That's probably more like the explanation. But it's still very much under investigation. So if you want to write a paper on that, feel free. Right now, there are a lot of ideas out there. Yeah.
How do the elliptical orbits of these planets affect your calculation?
So ellipticity is not something we can get a good handle on with just Kepler data. So you're just getting one tick. In the transit timing variation situations, you get a better handle on eccentricity. Basically, in a packed system like this, they can't be very eccentric, or that would be chaotic, right? So they're all pretty close to circular in this kind of system, but they're not exactly circular. And there's a ton of dynamics papers on how eccentric can it be before it'll destabilize, et cetera, et cetera. Okay, well, let me get to the meat of it. Earth-sized planets, right? That's what we really wanted to know about. I just wanted to show you how hard that is, even with Kepler. Okay, here is the detection of an Earth-sized planet. If you just look at the black dots, those are all the individual measurements of the brightness of the star folded to the period of the planet after we figured out what that is. Okay. If you just looked at that, you might or might not realize that there are fewer dots here and more here than there. The blue dots are, when you start averaging a lot of points within a time bin, you get a much better signal. And the red curve is a theoretical transit model that fits through those points. Right? So it's not easy. And this is a relatively bright star. If you have a fainter star, basically the points just get noisier. Yeah.
So you said you need at least 3 transits.
Right.
Those measurements look like hundreds. How many transits are represented amongst those measurements?
That probably is, because the orbital period is 6 days, so it probably is 100 transits. Right. So. So now you're prepared to understand that finding an Earth analog ain't so easy. So suppose you only had 3 transits there. So the Kepler mission lasted 4 years. So the Earth analogs will typically have given us 3 transits. I frankly don't actually expect us to find an Earth analog, a true Earth analog. On the other hand, we do find Earth-sized planets at various distances, not particularly far from their stars, but there's no reason to think that that's special in some way. As long as the distribution of Earths seems to be kind of uniform there's no reason why it shouldn't extend out to 1 AU. But that is the argument that I think will come out of this. So we'll know how many Earth-sized planets nature likes to make. We won't have actually found one that is at our distance from a star that's like ours. That would be my guess. Although it could happen, but we have to be lucky, basically. So you need a bright star to do that. Let me skip this because we're starting to run out. So here are some of the planets that we have found. And apropos the comment about Jupiter's moons, here is Jupiter and its 4 Galilean moons. And to scale, this is an M star, which isn't a lot bigger than Jupiter, and 3 planets that are definitely rocky planets, kind of all on the same scale as the Jupiter system. So, you could make an argument about semi-common formation there, at least. And then here are some other ones, So here's the Earth, and all the rest of these are confirmed Kepler planets, and there's Mars. So we definitely reached the terrestrial zone and got rocky planets. And in fact, it's gotten even better lately. So this is the Earth, and then here are 2 planets in one system. This one is a little smaller than the Earth. There's Mars, there's Mercury, and here's a 3rd planet in that same system, which is actually smaller than Mercury. Now that's a really favorable system. It's a very bright star, and it's got these 3 planets, and this one has a really short orbit, tons of transits. But that's probably the record. That'll probably be the record holder. So smaller than Mercury in the most favorable circumstance. There's no question, though, that Kepler has found terrestrial planets and in reasonable numbers. And actually, right here at Berkeley, a graduate student working with Jeff Marcy developed a slightly better technique for finding Earth-sized planets and found a bunch more. So basically, this almost doubled the sample of Earth-sized planets at the beginning of this year. The crosses are false positives, but the rest of them look pretty good. So here's one Earth radius here, and there's a bunch that are Earth radius or smaller.
This is still Kepler data?
This is all Kepler data, yeah. You'll notice that the size bars, error bars, are different. These are ones where we only know the size based on stellar spectroscopy. But in some cases, it turns out Kepler is also good at one other thing, which is called astroseismology. So you can measure, the stars quiver. I said they vary for various reasons. One reason is that they quiver just because they're noisy and they kind of ring like a bell. And Kepler actually can see that too. And if you measure that carefully, you can get the size and density of the star just from that. And so the ones with small size errors are ones where Kepler has also given us a better size on the star. Well, the net result of this is the following. So the other thing Eric did here was, and this is going to get done again better, especially now that the mission has sort of ended gathering data. There's a lot more work left to be done, but one of the biggest pieces of work is a completeness study. So if I take Kepler stellar data and I insert an Earth-sized transit signal into it, and I run it through our data pipeline, what are the chances that I find it out the other end? So how complete is that search, given that the data is really there? And this is kind of the answer right now. So here's one Earth radius here, up to 5 point something. And the color is a completeness signal. So basically, if it's blue, it's basically, you can find them all. And if it's red, you're really doing poorly on that. And so you can see, this is orbital period here. So we do worse as you get to longer orbital periods. Why? Because there are fewer transits, basically. And you do better as you go to larger planets, just like you expect. And so right here in this sort of 20 to 50 day bin, at the size of the Earth, it was 50% complete. Now, right? So we're probably missing half the Earths that are in there at this point. So you could just say, okay, whatever number I get, I'll multiply it by 2, right? Which is fair enough if you've done your completeness analysis properly. Or you could work on finding those other 50%. But anyway, making corrections based on this completeness analysis. This is how many planets there are out there. That's what this talk was about, right? But now with some caveats. So this is the fraction of stars that have planets with orbital periods between 5 and 50 days. So being always careful to remember that. This doesn't tell you about planets that have orbital periods of 2 years or whatever. Okay? About 0.3% of planets, of stars. And so now this is corrected for all the other effects that I talked about too. The likelihood you'll see a transit, how good Kepler is, how many stars we have in our sample, everything. So we think the fraction of stars that have sort of Jupiter-sized planets in these orbital periods is low, less than 1%. Between 2.8 and 4 Earth radii, it's kind of low. Well, whether that's low or not depends on your prejudice. 1.5%. Up here, this looks kind of constant at something like 8%. So this is super Earth. These are mini Neptunes, basically. These are probably mostly mini Neptunes as well, and these are Earths and super Earths here. But what does this mean? So let's say it's 8%. 8%, so if I pick a star at random, I have an 8% chance that it has a super Earth or Earth in an orbital period between 5 and 50 days. Okay, well, what about the next? What about between 50 and 100 days? Maybe another 8%. Maybe this doesn't keep going out, but as far as we can tell from planet formation, it ought to go out to, a few hundred days at least. So that's a large number, 8%. But essentially that means, probably something like 50% of stars have planets, in what we would call the inner solar system, say within the orbit of Mars or something like that. 50%, well, how many stars are there in the galaxy? 300 billion. So 50% of that is 150 billion. And that's the, I gotta go to the end here. That is the fundamental result of Kepler, and which I think is a solid result. Most stars, so when you look up at the sky, most of the stars you see have planets around them. And many of them have Earth-sized planets around them. And the total number of such planets in our galaxy is billions and billions, like Carl Sagan used to say. At this point, I think that's a pretty solid result. Okay? Also, the super Earths are an important size of planet, so there's nothing, our solar system is a little weird not to have a super Earth in it, or a mini Neptune. They're pretty common as well. And then if, I didn't talk about the habitable zone, but, if the Earths are in any way uniformly spread out to 1 or 2 AU, then there are plenty of them in the habitable zones as well. And so the other way to look at that is then the nearest habitable Earths must not be too far away from us. Maybe within 50 light years, one would guess. There must be at least a couple of them. And so that's the fundamental result from Kepler. Now, what do we need to do now? Well, we really ought to try to get further out. So outer planets, we need new methods to get to those outer planets. The next mission, now that Kepler is dead, the next mission will be to try to locate some nearby planets. So it's called TESS. It will be an all-sky survey, unlike Kepler, which was a pointed survey. And it will only look at the brightest stars, which are the ones close to us. But it will use the transit method as well. It won't stare for years, so it won't find long period planets in that survey either. So we'll still get short orbit planets. But they'll be close to us. And then we can hope to study them in other ways. We also have begun the study of planetary atmospheres. It turns out if a planet transits, then a little bit of the starlight actually goes through the planet's atmosphere. And if you're really good, you can measure that as well. And so about 10 planets, they're all giant planets, have had some spectral information gathered from their atmosphere already. So that's certainly a hot topic at the moment. And then finally, we will be able to take images and spectra of nearby rocky planets, but I'm guessing that's going to take 20 or 30 years before we get there. So I'll stop here, and thank you very much. Yeah.
I was just wondering, did people have sort of an estimate of how long the Kepler telescope would last, or?
Well, the primary mission was funded for 3.5 years. Originally, it was going to be 4 years, and then due to budget constraints, it got moved to 3.5 years. So that was what NASA said to the contractor who built the spacecraft. So this needs to last for 3.5 years. So the contractor is safe. It lasted for that. we wished it would have lasted somewhat longer, but the warranty was over. So, yeah.
Can they make another mission for the telescope even though it doesn't move?
Oh, that is under very active consideration. So when the wheel failed after a few weeks, the Kepler folks said, this is probably not going to work again. They issued a general call to astrophysicists. Can you think of something else we could do with this telescope sitting out there? Given that we're not going to be able to point it with the precision needed to get the primary mission done. So that there has been a white paper call for the last month and a half. I think the due date is maybe the end of this month. Then there will be some committees convened to read everybody's ideas. Basically, what's possible is with two wheels, you can point kind of well, and then actually turns out the solar, not solar wind, but just light pressure from the sun tends to push on the spacecraft and push it over this way. And you can use the wheels to push against that. And so we can point it but it'll have more jitter than we can live with for the exoplanet search. So the question is, should we use it in that mode, and what should we be doing at that point? And so lots of ideas have come forth, and NASA will decide whether it's worth the money to run the mission, given what kind of science comes out of it. But that process is underway. Yeah. Oh, sorry.
Okay, sure, go ahead.
What are typical distances to the Kepler planet?
Typically, they're several hundred light years. I'd say 1,000 light years is a typical distance. So we're not going to be studying those planets much further. Really, the point of the Kepler mission was to determine the frequency of planets. And since the frequency is high, it means really we ought to find nearby ones and study those. And so that is where this is going to go. Yeah, in the back.
This is for our galaxy, the Milky Way.
Right.
Correct? What percentage of all the stars in the universe are the stars of the Milky Way galaxy?
It doesn't matter. A very tiny percent.
You want to have a maximum number for the possible planets that you can find. 10 to the 40th power would probably be a good estimate.
Oh, that's probably too high, but
it's less than that, right?
Right.
So I'm saying, what you're saying is that the star, it's a very small percentage, like say 10 to the minus 30. I mean, I'm just trying to guess.
Well, I think the right way to do that is to say there are, let's say, 100 billion stars with planets in our galaxy, and there are 50 billion galaxies in the observable universe. So you can multiply 100 billion by 50 billion, and you'll get some number, and
no matter how many
that's a reasonable guess.
Planets that are relatively close to us, there's going to be an awful lot more that are far away from us.
There are more planets out there than you can possibly think of anything to do with.
But far away.
Yeah, most of them are far away, exactly. Right. So, from the point of view of studying them, we really want planets that are within 100 light years of here. So that number is not large, but it's reasonable. But yeah, I mean, so there's nothing special about the Milky Way galaxy.
But the fact that the percentage was high, that was...
Yeah, I think what that tells... It tells you that the universe likes to make planets. And so there are zillions of them everywhere, basically. So I gather the organizers would like me to stop the formal part. So I'm going to tell you how the mission works, and then I'm going to tell you what the main results of the mission are. That's basically my talk today. So how does it work? Well, first of all, this is the Kepler telescope, and those of you who still read newspapers or check the news on the net this week will have read that unfortunately the Kepler mission is now defunct with respect to its primary mission, that is the mission of figuring out how many planets there are out there. It did fulfill its goal of doing a study for 4 years. So we got 4 years of good data, and then the gyroscopic pointing controls are no longer working on Kepler. This picture actually is correct in the sense, you'll notice here's the Earth and Moon. Kepler is not orbiting the Earth. It's actually in solar orbit. It's trailing the Earth. It's gotten about a third of the way behind us in our orbit at this point. So that's where it does its work from. So basically from Earth orbit, but not from around the Earth. And it's just a telescope that looks out. And I'll explain how it works. But what it's looking for is, in a way, what's in this picture. Although naturally it cannot resolve stars in the way that this picture shows. So this is our star, the sun. That's a shadow of a blockage caused by a fisherman on a pier. That's a pelican. These are clouds, and that is the planet Venus. So that is an Earth-sized. See, a transit is just the diameter of the star divided by the diameter of the planet's orbit. That's the chances that you will see a transit. And so for the Earth, which is a couple hundred solar radii away from the sun, the likelihood that somebody sitting in some random star system elsewhere would see the Earth transit the sun is about 0.5%. So that's good news and bad news. That means that it's not very likely that it will be seen. On the other hand, if you see it, then you can say, that only happens, I only see 0.5% of these, so I get to multiply, every time I see one, I get to multiply that by 200 if I want to know how many planets there are out there. Okay? But the number I get to multiply by is this factor here. So for very close-in planets, the diameter of the orbit is that much bigger than the diameter of the star. The probability can get up to something like 10%. So we'll see 10% of planets which orbit with few-day orbits around their stars we can detect with the transit method. Okay? So that's the one thing. What that means in terms of mission design is I better look at a lot of stars, because for most stars that have planets, I'm not going to see a transit. The second question is, what am I going to see? So I do not see a stellar disk when I look at the stars of the telescope. All I see is a point of light. And there's no chance at the moment that we're going to resolve a disk and see a planet and in the process of transiting the solar disk. And that is the methodology that Kepler uses. So we are looking for that event to occur around other stars. But of course, stars are all just points of light. And so I'll explain how it uses transits to find planets. This is really the only good way right now we have of detecting planets the size of the Earth. The other methods that are used don't really work for planets that small. So let's talk first about transits and how you use them for detecting planets. The concept is really simple. If you are so fortunate as to be sitting in a place where you see a transit actually pass in front of the star that it's orbiting, then it's going to block some light from the star while it is projected onto the stellar disk. And of course, that won't necessarily happen. In fact, most of the time that won't happen. Planetary systems in the galaxy are oriented randomly with respect to any coordinate system you want to think about. So they're not all aligned with the Milky Way. They're certainly not all aligned with our solar system. They're pointed in arbitrary directions. And so for most planetary systems, the planets are in an orbit where they'll never appear to cross in front of their star as seen from the Earth. But it's not hard to calculate how likely it is that that's going to happen. I'm not going to go through the math here for this audience, but let me give you the answer. The answer is the probability that you will... Thank you, everyone. This talk is always a pleasure to give, and I want to encourage your questions during the talk. sometimes I get too many questions, and then I'll say, okay, we'll talk more about that at the end. But in general, please ask if I'm going along and you're either not understanding something or you just want to know more about something. I think this is NASA's most exciting mission of the last few years, maybe along with Curiosity and other Mars rovers. But it certainly this is a time in the history of humankind where we are, for the first time, learning about planets, how many planets there are out there, how common or rare is a planet like the Earth. I was a science fiction fan growing up, and I still am, actually. And so that's a real big question. I used to watch Star Trek. They didn't have any trouble finding planets to investigate. And the question was, is that pure fiction or is that probably the way it is? And so the Kepler mission really was designed to answer that question. Probably many of you know that we actually haven't known about any exoplanets until 1995. And then for a while, the methods that we were using to find them really concentrated on large planets, gas giants like Jupiter, especially if they were close to their stars. So nothing like the Earth, really. And the Kepler mission really is the first major mission to be able to study the question about what about terrestrial or rocky planets. Like I see a little black dot moving across it. That's not what we're looking for. What we're looking for is just the effect of that. So this is called a photometric light curve. That just basically means a history of how bright that point of light appears to be. And so the star, if we assume the star has constant light, which is not a correct assumption at the level of precision Kepler has, but start there, then it's just going to be constant. And then we'll just notice that suddenly the light decreases, and then after a little while it increases back to the former rate, and that's it. So that's the signal we're looking for. So that just means that the Kepler telescope needs to be very good at measuring how bright stars are. It needs to measure them to quite high precision. I'll say how high in a minute. Do you have a question? Yeah.
Yeah, is there a common factor to determine the distance of a planet is from the star, its surface, like mass? Is there any common variable?
There's nothing to say how far a planet is going to be from its star. In fact, that information is part of what we learned from the Kepler telescope. So what we learned basically is I'll explain how we learned that. But that is one of the things we find. So we are being told by the data what the distribution of planet distances is. There's no theory that tells you what it ought to be. Okay, so how much of a dip is this? It turns out it's also very simple to figure out how much of a dip it's going to be. It's just the area of the planet